introduce our postdoc, Ryu-Makia, AJ. And yeah, I think many of you already know him pretty well, but let me briefly introduce his academic history. So Ryu has got a PhD in Kyoto University in 2013, working with Professor Tomonori Totani, working on cosmic ray related galaxy formation. And after graduation, he got a JSPS postdoc fellowship at Tokyo University from 2013 to 2016. And at 2016, he kind of joint postdoc between ITMU and ITMU in Japan and MPA in Germany, working with Eiichiro Komatsu, with the director of MPA. So originally he was working on a cosmic ray, but his research are going to broad and also going to the large scale, so from galaxy formation, galaxy evolution, and now cosmology. And currently he's working here as a postdoc since 2020, primarily with Hirashita-san on the cosmic dust, and also he often doing activity related to cosmology, so his research is pretty broad. As I said in the email, so AJI is involved with the so-called PFS project, and one main project is cosmology, and he's a chair of the cosmology working group, so he's serving a very important role in this project, and so he's the best person to listen to the cosmology research related to PFS. So he will tell us about cosmology about PFS. Please welcome.
Okay, thank you for introduction, Teppei. So, I'm Ryu-Makia, and as Teppei introduced, I'm leading the PFS Cosmology Science Working Group. I'm co-leader. There is another leader, Tomomi Tsuneyama in Nagoya University, Japan. And so unfortunately, I already decided to move out from academia to industry. So maybe this will be my last talk in astrophysics. And so it means that I will also left from this working group. But the purpose of today's talk is to give you the overview of the PFS cosmology program. And if you're interested in this program, feel free to ask me if you want to join the science working group. There is a lot of remaining works, and we are going to get the real data within 2 years. So very interesting era is coming. So it's nice timing to join the working group. So working group is still small, so maybe you can join the main program of the PS cosmology, or you can do some primary work for this cosmology group. So yeah, if you're interested to join, feel free to ask me. And Teppei is also working for the PFS cosmology science, so you can also ask Teppei. So okay, let's begin. So yeah, as I think many of you know, but let me begin with the introduction of the PFS. So PFS is the SBAR prime focus spectrograph. So this is the SBAR telescope. So and this is the prime focus instrument, and there is spectrograph. And those spectrograph and this instrument is connected by the optical fibers. And there is many fibers, which is called COBRA. So the PFS point those optical fibers to the position of the galaxy and get the spectrum of those galaxies simultaneously. So, and this instrument has 2,400 fibers. So the field of view is about 1 square degree. So this instrument can get the 2,000 of spectra in one exposure. So this instrument can allow us to scan the sky very quickly. So so which is very good to perform the survey. And so this is a wavelength coverage, so optical to near infrared, and we are planning to conduct 3 science cases in our groups, working groups. So we have 3 main topics: cosmology, galaxy evolution, and galaxy archaeology. And also, this is the open use instrument, so you can also apply the proposal, observation proposal, to use this instrument. So if you have some good idea, you can apply. But instrument is still under construction, and we are planning to have the first flight in 2024. Okay, so feel free to interrupt me if you have questions. So this is the PFS, and this is PFS collaboration. The main institute is IPMU in Japan, but there's many collaborators in Asia, US, and Europe, and the AGIA is one of the major contributors. So both in the science and both in instrument development, there are so many members, and they are hard working for constructing the instrument. And now the PFS is intensively tested in the Mauna Kea. So yes, so this is overview of the collaboration. So this is PFS is open use, but PFS collaboration is planning to do some large survey, and we are writing the proposal for the Subaru strategic program. So this is a program for the large survey. So previously, HSC and Subaru HyperSpringCam already done some large survey in this program, and next PFS will do the survey. And so, as I said, there's cosmology program, and the galactic archaeology program, and the galaxy survey program. The cosmology and GA and GE, and we have 3 major sciences, so testing the lambda CDM, and study the assembly history of galaxies, and study the importance of the intergalactic medium. And the cosmology target of the cosmology program is written in the blue text. And for example, one of the main goal is to study the nature and the role of neutrinos, and study the expansion rate of the universe, and test the general relativity, and test the curvature. And the cosmology also, data of the cosmology also used to study the galaxy assembly history of galaxies, because the PFS can provide the large data set of the spectroscopic redshift to the HSC galaxy, and not only the redshift, but also some lines from star forming region, or some so the PFS data, even the cosmology data can also use to study the galaxy evolution. So anyway, this is an overview of our Subaru PFS strategic program. And today I'm going to talk about this cosmology survey. So in this survey, so we are going to scan the sky area of this region and this region. So this is the north half of the sky, and this red region shows the HSC wide field. This is already scanned by the HyperSpringCam, and there's a lot of high quality photometric data here. And the PFS cosmology scanned the same region, but this time we are going to get many spectra and determine the redshift, and we will get the 3-dimensional map of the galaxies from those data set of spectra. So we will observe the 4 million emission line galaxies at this very, very wide redshift range. Okay. And so so what we will do is that 3D map of the galaxy. So we have two major science goals. So one is to measure the neutrino mass. So this is so I'm going to talk in detail later, but our goal is to achieve this sensitivity to the total neutrino mass 0.02 electron volt. This sensitivity means that if the neutrino mass, so now we know that the minimum neutrino mass, total neutrino mass, is about 0.06 electron volt. So if we can achieve this sensitivity, we can detect the neutrino mass at 3 sigma. And if the neutrino mass is more higher than that minimum mass, so the sensitivity also larger than 3 sigma. And so this is kind of guaranteed science. We already know that the neutrino has mass. We still don't know the absolute value of this mass, but we know that how it affects the structure of the large scale structure, and we can perform the forecast to this sensitivity, and we get this value from simulation. So this is kind of guaranteed science. If we can achieve the planned sensitivity of PFS, and if we can control the systematics as we planned, so we can surely achieve this goal. So this is one of the main topic of the PFS cosmology. And the another goal is, so this is of course related with each other, but another topic is that to perform the end-to-end test of the universe. So this means that we have precise observation of the C and B with double map and Planck, and the observation of C and B provides us the initial condition of the universe. And if we assume that the flat lambda CDM model is correct, we can evolve that initial condition to present. So we have the history of the universe. But recently, some observations suggest that there is a discrepancy between this initial condition observed by Planck and or double map, the CMB observation, and the observation in the current universe observed by the Cepheids and supernovae or large-scale structure. So there is a discrepancy, maybe. So it means that this end-to-end test of the universe failed. So there is some failure in the flat lambda CDM model. So the PFS, another one of the goals of the PFS cosmology is to perform this end-to-end test of the universe by also observing the redshift 0.6 to 2.4 and study the evolution of the universe as a function of time, and to investigate the lambda CDM scenario. And so this topic also, so lambda CDM works well, but maybe there is failure. And we don't know almost anything about this lambda dark energy. So to study this lambda or dark energy or modified gravity is another very, very important topic in the cosmology. So through this end-to-end test of the universe, the PFS can also study the dark energy and the modified gravity. And maybe we will find something new, some new physics. So this is a discovery potential. We don't know what we found, but what we find, but there may be some new interesting something. Okay, so this is a major two science goals of the PFS cosmology, and so how we will achieve this goal? So we will use those observer bubbles. So as I said, we will get the 3D map of the galaxies in wide redshift range, and in this range we will measure the galaxy autopath spectrum or correlation function and the galaxy bispectrum and also size function of the voids, and we will also observe galaxy lensing cross-path spectrum. So this is great synergy with HyperSupreme. Okay, so this is overview. So let me talk about the neutrino mass more in detail. So from the experiment, but neutrino oscillations or solar neutrinos, there's many observation and experiments for neutrinos, and we already know that the neutrino has 3 mass eigenstates. So neutrino has 3 flavors, so mu, E, mu, and tau. But besides this, so neutrino also has 3 mass eigenstates. So there are 3 species. And currently, we only know the squared difference of these 3 mass eigenstates. We don't know the absolute value of the total mass, but we only know the difference between the different mass. And we can, there's 2 possible solutions. So this is, one is the so-called normal hierarchy. So from experiment, we know this mass difference, between 1 and 2, and sorry, do you have battery for this?電池切れちゃった。Yeah. Oh. I see. Oh, size is different. 棒ありますか?
You can point by finger.
Okay. So yeah, there is 3 species, and we only know this mass difference. So yeah, it's very easy. So we can think about 2 cases. So this 3rd species is massive or lighter than those 2. So this is the so-called normal hierarchy, and this is inverted hierarchy. And yeah, if we can measure the absolute value of total neutrino mass, so it carries the fundamental information for not only the cosmology but also particle physics. So this is very, very important. And yeah, so this absolute mass scale determines the nature of neutrinos. So this is also closely related to the how to say, matter antimatter problem or CP violation. So this is a fundamental problem. So, but how the cosmological data constrain the neutrino mass? So yeah, from the past studies, we know that the massive neutrinos affect the structure growth in two ways. So the first is that so we know the number density of neutrinos, but if the mass of the neutrino changes, it means that the energy density of neutrino changes, and it affects the expansion rate of the universe through the Friedmann equation. So it changes the expansion history of the universe, depends on the neutrino mass. And another thing is that so after the neutrino turns to the non-relativistic particle, they still have very high velocity, so they cannot they cannot collapse into the halo, or they cannot trap in the halo. The halo. So this affects the growth rate of the small scale structure. So in this two ways, the massive neutrino affects the power spectrum, so of the density field, or the galaxy density field. So okay, and this is the simulated galaxy power spectrum, and this black line shows the model with neutrino mass of the 0.06 electron volt, and this dashed line shows the 0.2 electron volt. So if the neutrino mass increase, the amplitude decrease. So by observing this effect, we can constrain the massive neutrino. But this effect also degenerate with other parameters like the sigma 8, which is the amplitude of matter power spectrum, or AS, the amplitude of primordial density fluctuation. Or it also degenerates with galaxy bias. So it's not easy to measure this effect. So plotting like this, so it looks easy to detect this difference, but we need careful observation to determine this massive neutrino. Okay, and this is the current best constraint on the neutrino mass from the cosmological data sets obtained by EBOS program. So let's see. This blue line shows the constraint on neutrino mass, and this is a 0 point. So left side, this area is unphysical, but they just plot to show that the peak of the distribution is in the unphysical region. So this figure shows that they constrain neutrino mass almost less than 0.1 electron-volt. So this 0.1 electron-volt is the threshold between normal hierarchy and inverted hierarchy. So they seem to achieve that threshold, but still this probability, so this PDF shows that some peak is unphysical. So it means that some statistical fluctuation, because of some statistical fluctuation, the mass constraint on neutrino mass is very tight. So I mean to say that the constraint, this constraint is not enough to distinguish the normal and inverted hierarchy, or to say that we detect the neutrino mass from cosmological data. So this is the current situation, and this is the forecast for PFS. So this, let's see, this magenta line, this is the best constraint forecast from my simulation. And this constraint comes from the combination of the Planck and the Bose and the HSC and PFS. And this figure shows that we can detect the Newtonian mass with about 3 sigma. And we can, if the minimum mass of neutrino is 0.06, we can say that we can distinguish the normal and the inverted hierarchy in like 2 sigma. This is the power of the PFS. Okay, so let me talk about again the end-to-end test of the universe. So as I said, we already have the precise measurement of the initial condition of the universe, CMB, and we can evolve this initial condition with lambda CDM, and we can compare the present day observations like SHOES SN1 survey or SDSS large scale structure survey. And PFS put a new data set between initial condition and current data by observing this redshift range. So, but so the lambda CDM model works very well, but there is 2 possible failure found in recent dataset. The one is the so-called Hubble tension. The value of the Hubble constant predicted from the CMB and the lambda CDM data doesn't match the local measurements like Cepheid supernovae, so obtained by, for example, Riess et al. There's another tension in the density fluctuation amplitude. So this is the so-called S8 parameter. This is a combination of the sigma 8. So this is amplitude of density fluctuation and omega matter, the density of matter. So this S8 parameter is amplitude of density fluctuation. Well, so this parameter doesn't match with the CMB and the more late measurement in the late-time universe obtained by the weak lensing or galaxy clusters. So this is another tension. So, okay, so I'm sorry, this is a bit old figure, but this figure shows the tension in Hubble constant. So this red point shows the measurement from the Planck, and this blue point shows the measurement from other local astrophysical measurements. So Planck best fit is about 67, but best fit from the local measurement is about 73. So there is high, there's mismatch in the high significance. And another tension is that this S8 parameter. So so this is also a bit old, but okay, so this x-axis shows the omega matter, this y-axis shows the S8 parameter. So here they call the clumpiness of the universe. And those red and green and gray contours are constraints obtained from the weak lensing measurement, and this is a Planck. So there is mild discrepancy between those lensing observations and Planck. So this result may show the failure of the lambda CDM model. So this is another tension, and this is not so famous, but there is another tension. Okay, so this figure shows the relation between omega matter and the Hubble constant, and the constraint on this relation obtained by the baryon acoustic oscillation measurement from galaxies at redshift less than 1, and from quasar and Lyman alpha forest at a redshift larger than 1. So there is discrepancy in omega matter value. So if the lambda CDM model is correct, they should match perfectly, but there is some discrepancy between high G observation and low G observation. And PFS have the wide redshift range, so PFS can address this problem with single tracer. So the problem in this figure is that the tracer of the BAO is different for low G measurement and high G measurement, but PFS can do the same analysis with similar analysis with single tracer. So maybe without raw systematics, like this. So this is another thing the PFS can address. So okay, so and the last thing is the study of the growth rate of the structure. So this y-axis shows the growth rate of the structure, how the efficiency or speed of the growth of the cosmological structure shows as a function of redshift. And there are many existing observations. And this red points are the forecast for PFS. The only PFS can address those high redshift points. So this green and blues are other large-scale structure survey in the same generation. So DAISY and Euclid. The PFS will be the only player at this high redshift range. So this is one of the uniqueness of the PFS. Okay, I have 30 minutes. Any questions? Okay. So, but yeah, as I said, there are another and similar large-scale structure experiments, like DAISY performed in the groups in US or Euclid, and also LSST and Roman. So there's many rivals in the same generation. So what's the uniqueness of PFS? So we ask ourselves, and the uniqueness of PFS can be summarized into 3 points. So this large wide redshift coverage, and I haven't talked too much about this, but we have high number density. So, and which allows us to go to study the more smaller scales. And also we one of the most important things is that we have HSC. This is kind of world best quality of the photometric catalog, and so HSC is a great help. And HSC and PFS make the powerful duo. So HSC provide high quality photometric data and also the weak lensing maps. And the PFS can also provide important information, the spectroscopic information to HSC. So those points are the uniqueness of the PFS. And also I want to stress that we are not in the competition. So we are, I mean, we means the PFS and DAISY and Euclid, the same generation experiments are like in the complementary relation, because if we want to claim that we detect new mass, it's a huge thing, huge impact. And when we want to say such a thing, so we need to confirm the same results with multiple independent experiments. So in that sense, the PFS is still very important to perform this survey, even there are many other similar experiments. Okay, so Okay, so let me explain more in detail about some example of the PFS uniqueness. So I said that the high number density allows us to go into smaller scales. But another important thing is that the high number density allows us to identify the small voids, and the number density of galaxies is very important to correctly identify the void and its shape. And this figure shows that the number density of voids will be detected by the DAISY and the PFS. So at low redshift, PFS cannot win the DAISY because they have 10 times larger survey area, but at redshift, a higher redshift, because of the high number density, PFS can detect a significant number of the voids. So this is very unique aspect.
Sorry, but y-axis is number density. It shouldn't depend on the size of the survey.
Yes, you're correct. So yes. Okay, I'm wrong. Maybe. So okay, I forgot the details of how to make this figure, but at this redshift range, number density of DAISY and PFS is not so much different. So this is reasonable. Okay, thank you for correction. Okay. Okay. And another example of the uniqueness of our program. So we have HSC, so we can combine the PFS data and HSC data. And this is the observable called EG, proposed by the Penji-chan. So this is a combination of the weak ranging measurement and the redshift space distortion measurement. So this weak ranging is from HSC, and the redshift space distortion is from PFS. And by combining this, we can construct the model of the gravity very precisely, and without so we can reduce the systematic effects from the bias by combining these two measurements, galaxy bias. So this observable is also the unique point of the PFS. Okay, so next I want to introduce what we have done so far, maybe what we have done for the PFS project. And later, I want to briefly talk about what we will do for the PFS. So because we don't have real data yet, so what we have done is just preparation for the survey. So first, we need to set the goal of the survey. What's the main science of the survey? So neutrino mass, dark energy, gravity. And the next thing is to do is assess the feasibility of survey. And prepare the survey proposal if needed. So to do this, we have developed the simulations, the mock catalog for target selection, the perform systematic study, and many other things. And also we perform the likelihood analysis, like the Fisher forecast, or perform the MCMC using the simulations, and we use these results to design the survey parameter. So this is a very brief summary of what we have done so far. So let me introduce these things. So for simulation, we have developed the so-called log normal simulation for the PFS. And this is first developed by the Aniket Agrawal who is the former postdoc at AGIA in 2017. So, and this simulation quickly generates the mock galaxy catalog. So this is kind of random realization of the density field, but which follows the log normal distribution and the input path spectrum. And we also calculate the velocity field and the galaxies. So this simulation can be used to study the power spectrum in redshift space. And a good point of this kind of study is it's very quick, so we can easily generate the thousands of realizations of simulation. And another good point is there's no numerical uncertainty and complexity, because this is just a random realization, so we know the answer. So this is the one of the output of the simulation, and this figure shows the power spectrum monopole in redshift space, and up to very small scale, k equals 0.3. So this is small scale, large scale, and this line shows that simulated data points very precisely follow the theoretical models. So because of this nature of this simulation, we can use this kind of simulation to test the non-physical systematics, non-physical effects, unphysical effects like survey window function or effect of fiber assignment without caring about the complex physics, particularly at those small scales. So this is one of the achievements, our achievement. And we also constructed the simulations for the weak lensing and the galaxies. So this is the so-called log normal lens. So this simulation is based on the log normal galaxies simulations, but in this time we have constructed a light cone, so by combining the multiple outputs realizations of the log normal simulations from redshift 0 to 3.2 to mimic the weak lensing map of the HSC like this. So this map shows the contour of the weak lensing map. So so by constructing this kind of simulation, we can simultaneously simulate the HSC outputs and the PFS outputs, and we can also study the systematic effects, not only for galaxy auto path spectrum, but weak lensing path spectrum and weak lensing and the galaxy cross path spectrum. So this is one achievement. Yes, and this is outputs of our log normal simulation for galaxy and lensing path spectrum. So this is combination of the PFS and the HSC. And the simulation shows that we will be able to detect this cross path spectrum even at higher redshift with high signal to noise ratio. Okay. So yeah, this is one of the applications of the simulation. So by using the simulation, we can know that we can surely detect those signals. And based on those outputs, not only the galaxy lensing path spectrum, but the galaxy auto path spectrum I have shown. So we also perform the likelihood analysis. So by comparing the simulation outputs and the theoretical model, we can obtain the how the PFS cosmology program, how can PFS cosmology program constrain the cosmological parameters. And this is the details of our model of the galaxy power spectrum. Let me skip this. So yeah, we include the RSD effect, Kaiser effect, Alcock-Paczynski effect, and okay, sorry for many texts, but and for covariance, we have estimated from the simulation covariance of the galaxy auto power spectrum, the lensing cross power spectrum. And so this is the total likelihood. So this is galaxy auto power spectrum, the cross power spectrum, the bispec void, HSC auto, Planck, and the EBOS. And we have performed the Markov chain Monte Carlo analysis and get this kind of results. So this panel shows the constraint on Newton mass. From such an analysis, we obtain these results. So PFS, when we combine the PFS and the other existing experiments, we can achieve this goal of the sensitivity. And another finding is that the Newton mass constraint are tightly correlated with another parameters such as optical depth of CMB or primordial amplitude of the density fluctuation like this. It means that those parameters determines the amplitude of matter density spectrum at late time universe. So it means that the constraint on the Newtonian mass in the era of the PFS is limited by the uncertainty in CMB observation. And because of this, PFS and DESI, so and maybe Euclid will achieve the similar sensitivity in terms of the Newtonian mass, even though the survey volume or number density are different from survey to survey. So maybe in terms of the Newtonian physics, so future CMB observation for polarization to determine this tau will be very important to improve the sensitivity. So, okay. And next, let me briefly talk about our study of the systematics. So now we have we have developed the simulations, log normal simulations, and we used those simulations to perform the parameter forecast. But this simulation can also be used to study the systematic effects in the observation of the galaxies. So as I explained in introduction, the PFS assigns the optical fibers to galaxies to obtain the spectrum. But this is the field of view of PFS, and so it's hard to see, but each point shows, this is the zoom in, each circle shows the fiber. The fiber can only move within this circular region. So this limitation distorts the distribution of the galaxies from real distribution to the some distorted distribution. Okay. So we need to correct this effect to get the correct distribution of galaxies and to correct power spectrum and correct constraints on cosmological parameters. So this is important. So this is the power spectrum. These black points, data points, shows the power spectrum of true density field. And we find that after the fiber assignment, the power, so the amplitude of density fluctuation decreases to these blue data points. This is because the PFS only has a limited number of fibers in each field of view, so it suppresses the large scale density fluctuation above the scale larger than the field of view. So this effect is found in here. And because of the collision of the fiber, so the very close pair of the galaxy cannot observe in the same time. So this effect suppresses the correlation in very small scales. So this effect is shown here. So sorry, this is the ratio between the fiber assigned and the true power spectrum. So there is a separation in both large scales and small scales. And we have tested one correction, the so-called IIP correction, the individual inverse probability correction. So in this method, we weight galaxies by the probability to be observed of galaxies. So we assign the fiber, we run the fiber assignment scheme many times. And in this scheme, the fiber assigned to the galaxies, randomly assigns to galaxies within the circular region. So by running this scheme many times, we can get the probability to be observed for each galaxy. And by upweighting the galaxies with this probability, we found that the power spectrum is nicely recovered to this orange line, so almost unity. So this method works very well. But if we want to like the k equals 0.2 or 0.3, so there is still something uncorrected. So to correct those small scale separations, we need to consider the correlation between these IIP weights, or in other words, the probability of galaxy pairs to be observed, not individual galaxies. So this is one of the findings. Another thing is that, so such a thing has been already known, but we also tested that fiber assignment effect on the galaxy ranging cross power spectrum, and we newly find that the cross power spectrum is dramatically decreased by the fiber assignment. So this is before and after the fiber assignment. The signal goes to even negative on the very small. So the galaxy ranging cross power spectrum significantly affected by this fiber assignment. But still IIP works, IIP correction method works very well, and it recovers the true power spectrum almost perfectly. So this is our new findings. So and in this study, our simulations were very useful. So this is one study. Okay. So next, I'm going to briefly talk about what we will do next. So we developed the log normal simulation, and it is useful to study the survey systematics like the fiber assignment. But to perform the more robust analysis, we need to understand the nature of our target. Our target in PFS cosmology is the O2 emitters. They are the star-forming blue galaxies, and we need a more realistic model of our target. So to study those O2 emitters, maybe we need to construct n-body simulation, or hydrodynamical simulation, or semi-analytical models. And if we have those simulation, we can study the target selection or covariance estimation or testing the spectral analysis of the spectrum pipeline. But maybe for the covariance estimation, we need several thousands of realization with very high mass resolution and large box size. So maybe it's very still difficult. But yeah, we need to study those things. And we have done something so far. So this is very nice plot from the works of the Teppei. So this is the figure from Okumura et al. So first, we need to know where is O2 emitters. Especially in cosmology, it's important to know the relation between the galaxy and the hollow mass to understand the nature of our sample. And this figure shows the relation between hollow mass and the number of galaxies of O2 emitters obtained from the HSC observation. And this panel shows the result for the same quantity, but from illustrated simulation. And both simulations show that typical hollow mass of the O2 emitters are very small, 10 to 12 or 10 to 11. So we need to resolve the 10 to 11 hollow mass to construct the reliable simulations. So this mass resolution is still smaller, about one order of magnitude smaller than the typical hollow mass of the n-body simulations for the cosmological analysis. So this is a bit challenging to resolve such a mass. Anyway, so this is just one idea, but to resolve such a computational difficulties, we can use the AI, augmented artificial intelligence. So maybe we can perform the super resolution simulation to obtain the more smaller mass hollows, or we can generate the field itself from the initial condition quickly using the AI. And if we can we can construct these n-body simulations, these simulations can be used to the analysis of the real data. Like if we have such a simulation, we don't need to analyze the power spectrum or bispectrum, but we can directly compare the field of the simulated field and observed field while including all the systematics like survey window or fibers. So maybe this is one of the future. But yeah, we are still working on such as things. Okay, so this is summary. So this is what I want to tell you. The PFS is powerful. We will be able to detect the neutron mass, and it will be the significant. It will have significant impact on cosmology, not only cosmology but the particle physics and all physics. So this is very interesting. So if you're interested in the PFS cosmology, so please ask me to join. And in AGIA, we are regularly organize the SUMIRE meetings. So SUMIRE is the name of the project with HSC and the PFS. So if you are interested in, please join that meeting. So, okay, so I want to stop here.
So questions?
Thank you for the talk. So I'm just curious for the fiber assignment. You mentioned
Yes.
Right.
Uh,
But I would know that it's if it's due to the fiber collision or something, it will impact
Mm.
the small scale more than the larger scale.
So it's not fiber collision, but it's due to the limited number of the fiber within the field of view. So let's imagine that if we only had one visit, we can only observe the 2,000 galaxies each in field of view. And if we have the much more target than the number of fibers, the number of this scale is limited to the other. So number density will be constant at this scale. So it smear out the fluctuation at large these scales. So this effect shows that. Okay.
I'm actually curious, what's contributed to the volume of
Uh,
scale?
So this is tiling. So sorry. So this is hard to see, but it's a honeycomb-like structure. It shows tiling of the PFS.
So it's full on the edge of the.
Yes. Yeah, we can erase this if we have overlap or maybe. But yeah.
You mean the scale is corresponding to the size of this fiber one?
Yes.
Oh.
And we did another numerical experiment. So without using the fiber assignment software, but just divided this region into grid and select galaxies. And in that case, we haven't observed such a bump. So I think this is the reason.
So I have a technical question. In your MCMC results, according to the record you wrote down, you regard all the statistics to be independent?
Yes. That's a weak point. So ideally, we need to have the large covariance for all the observables. And we safely assume that the defined redshift slice is independent. But so another thing we found in the study of fiber assignment is that the fiber assignment creates the artificial correlation between different redshift slices because the fiber assigned to avoid other galaxies in other redshift. So maybe we need to take into account such effect. So, and of course, the bispectrum void, we need to, and HSC auto, we need to take into account cross covariance between them.
Your constant is pretty much overestimated. Do you know how much?
I don't know. So for our fiducial model, we don't include void, and the bispectrum doesn't improve that much. So maybe if we include the cross covariance between HC auto and the galaxy cross, it had some impact. So yeah, it's just technical limitation. To have large covariance, we need many realizations.
Is there at the beginning of the PFS survey, is there a validation component, or are you going to go straight into the full cosmology?
So we are planning to use some first 2 or 3 nights to fix the target selection, or we are going to use the data in some validation phase to study the target selection. This is so I haven't talked about much that, but this is one of the most important part of the survey. So we selected galaxies from HSC catalog within some color cut using G and R magnitude, and we adjust this cut to maximize the number density and signal to noise ratio of all the emitters. And currently, our estimate is based on the MOC Cosmos catalog. This is just one model, and there is no validation that that Cosmos catalog works at our target redshift, our target galaxies. So we are going to use first 2 or 3 nights to validate our target selection and to maximize the success rate of the observation. So that's a plan.
Is the field that validation basically the galaxy evolution field, or is it kind of separate?
No, cosmology field.
Okay.
So yeah.